Thank you so much, Sammy. I am absolutely delighted to be here over in Brisbane. No mai haere mai ko te McNamara tēnei. Kia ora, welcome. I am, so in English that would be just welcome. My name is Tim McNamara. Be well. I'm here to talk about a programming language that has been voted developers' most loved programming language for 7 years in a row from the Stack Overflow Developer Survey. And it's almost everywhere in like the tech space, and I'm hopeful to provide a little bit of insight as to why Rust is both an increasingly chosen option, as well as, let's say, like if you wanted to tinker with it at work, to kind of give you a little bit of an edge. A small shout out as well to Lily's talk that was just prior to this one. If you weren't able to see it, I'd really encourage you to look at the recording, and because I think that was the other piece of Rust content at the conference. Super. Okay, so I'd really like to start with this little snippet from the Stack Overflow blog from a consultant trainer called Jake Golding, which describes kind of like the one-sentence summary of why Rust. It's a solid step forward, and the downsides that come with that solid step forward are manageable. So I'm from New Zealand. We've got some good stuff there, like fly to the Concords, mountains. Once every 5 years or so, we have a cricket team that actually, gets selected and knows how to win a game, which is useful. But sadly, we haven't been able to figure out software. In fact, no one has really figured out software. If you were from a large software enterprise or company, and you were really, really focused on security and safety, you would find, if you dig into all of the CVs that you patch, that somewhere around 70% relate to memory safety. And this is a relatively consistent theme that has actually been independently discovered through multiple attempts. And it turns out that people have started to ask the question, like, could we do better? And by the way, Rust will actually eliminate the entire class of bugs related to memory safety without any additional runtime cost. There is no garbage collector. There is no runtime that is sitting alongside your program, kind of nursing things along and making sure that objects are happy. I'm just going to provide a tiny glimpse of Rust. It's very hard to introduce a programming language to people that probably have never seen it before. And so hopefully there's a relatively representative examples. I'm also hopeful that I'm not terrifying people with some crazy syntax. Okay, so allow me to kind of go through here. So we start with input. We've got an ampersand and some square brackets and then I32. So this is a read-only reference to some slice of integers. Rust is what we call a systems programming language. So it really cares about how wide in memory my integers are. So it's going to actually ask me to say that this is a 32-bit integer. My function returns another integer. Its body contains this iter method over my slice, which returns an iterator over every value in that slice, and then applies an anonymous function to every item and returns another iterator, which, by the way, so again, with the reference, or the ampersand is a reference to each item in the list. And by the way, it's read-only, which means that it's impossible either on the outside of this function in some other thread or inside this function to actually mutate that slice as we're going through. We then return the sum. So the sum at the end creates, it sort of collects up all of the integers that we're processing and then accumulates them towards the final integer. Rust is an expression-based language and it kind of shares some pieces from functional programming, and so there's actually no return keyword there is a return keyword in the language, but we're not using it in this function. Rust will return the result of the last expression in your function. Okay, cool. But let's say, okay, Tim, that was fine. But what I really want, what I heard Rust was really, really good at was parallelism and concurrency. And I said to you, oh gosh, well, you have to sort of spin up some threads and create a thread pool and then sort of synchronize so that you're sending all of your input data into, to kind of distribute those out. And it turns out that that's actually incorrect. There's a library that can do all of that for you. So rayon, what we're doing here is importing what we call in the Rust terminology, a trait, which might be an interface, or you might also think of it as an abstract base class. And we do something that kind of feels a little bit like, let's say, monkey patching that you might be used to from, say, a Ruby. And it turns out, though, that this is statically compiled, and we're actually kind of granting slices with a new method, par iter, which will do all of the bookkeeping related to creating the threads, sending the items from my input stream to those threads, applying those anonymous functions in parallel, and then accumulating the result in my sum method at the end. Okay. Don't panic. So this is a more complex example, but what we're doing here is creating a frequency distribution. What we're doing here is creating a map, or a dictionary if you're from Python, that has words on one side, and then the number of times that they appear in the input text on the other side. So we're sort of counting up each word. What I'm trying to demonstrate here, at least on the surface level, is that Rust can sort of feel high level, and it's relatively ergonomic to program in, even though what we've been promised or told, it's a systems programming language, and those are supposed to be difficult and complex. So what we start here is we initialize our hash map with its empty, and then we go through our text and kind of return some iterator of sub-slices of the input text, and then we go and check if there are any pieces of punctuation on the left or the right sides. We trim them away. So if the characters at the side, at each sub-slice on the white space delimiters are not alphabetic, then we remove them. We then go into the counts hash map and ask, is this word already in there? And if not, please provide me with a 0. And then I increment that count. It turns out that count is a mutable reference into the hash map itself, and so there's a dereference operator inside count, for that count variable as well. Again, we don't need a return keyword because the last expression, which happens to just be evaluating what counts is at the end, is the return of the entire function. But there are a couple of things underneath the covers that I really want to point out before we move on. One, again, this is a read-only reference to text. It's impossible for this text variable to be mutated while we are processing its contents. Perhaps more importantly, really, if you really care about memory and memory utilization, there are 0 copies in this method. At no time do we take some input text, some input slice, copy it, and then sort of insert that into the hash map. The only thing inside there is a pointer as the key, because it turns out that references happen to be implemented as pointers, and a U32, so an unsigned integer that's 32 bits wide. It can count up to about 4 billion. If you've got a very, very large text, this will overflow, go back to 0. So hopefully that isn't what you expected. Hopefully we're going to be in bounds. Just because I know that everyone's going to be super excited on how to pass their programming interview, I thought I would implement FizzBuzz as well and do it in a way that's kind of neat. So I start here with an iterator over between 1 to 100 inclusive, which is the equal sign, and then I take the modulus of 3 and 5, and if the remainder of those divisions are 0 on both sides, I then print FizzBuzz, and I guess you know how FizzBuzz works. I quite like this because it really shows that we can have these very elegant constructs inside a language that is compared to some other, so it's like a C++ or a Java, where we don't really have these kind of niceties. And Rust is late, or was late to the programming world, and was able to really provide programmers with what they call in the blog nice things, right? More important, though, than the programs you can write are the programs that you cannot write in Rust. So Rust is a more strict programming language. Remember that the reason why we can eliminate, let's say, 70% of security vulnerabilities is because there are some subset of programs which we are no longer allowed to write. And this one, or something similar, got me multiple times as I was programming, let's say in Python, where I would confuse the assignment operator with equality. I'll see if this will work. We're going to find out very quickly. If I try to do the equivalent thing in Rust. First of all, I get a syntax error, which is a warning saying, Tim, come on, this is Rust. You don't need the parentheses. You don't need the brackets. Then we get a type error. So it turns out that this program will refuse to compile. And this just provides a little bit of a hint at some of what's to come. The result of Rust is what we mentioned a couple of times already as an expression-based language. The result of an assignment is what we call the unit value, which represents, it's kind of like the none of Rust. In a Boolean context, that doesn't make sense. The only thing that we can provide to a Boolean is by Boolean I mean the if. The only thing we can provide to an if is a Boolean, and then, hello, we also get this really nice help message. Why don't you try the equality sign? And we can click run, and we're happy again. So it doesn't equal 24, so it doesn't print out question mark. Here's something that's slightly more complex. There's two halves to this program. One is sort of an initialization stage where we create an array list, which is a growable list of, in our case, integers in Java. We insert 1, 2, and 3. The second stage is a check. We print it out, and then we kind of do some processing, and towards the end we print it out again and see what's changed. Hopefully everyone's seen the bug. We can't iterate over the list and also remove things from the list at the same time. Java-C will happily compile this. It will explode at you at runtime. It will have you'll encounter a runtime exception. Rust will be a little bit more pedantic. So here the equivalent is what we call a vector. And we push instead of add, so that's all fine. We try and print numbers, and then we remove the first item of the list of numbers, and then we print it out again. So let's try and compile this guy. And then first we can, again, another warning about style. Let's ignore that for now. And then we get this big kind of horrible error message talking all about movement and borrowing and ownership. It's saying that if you really, what this is saying is, actually, I'll make it a little bit more explicit. A for loop in Rust is sort of syntactic sugar for a method called into-iter. And into-iter, so we're attempting to take the numbers vector and turn it into an iterator over the vector, actually takes what we call ownership of numbers. And that's a problem because when you are the owner, it's your job to remove things. And in a sense, and so Rust is saying, hello, Tim. You can't iterate across something and also mutate it at the same time, or at least you can't change the number of items, the number of elements in the list. That's not something that is a valid move. It's giving me some advice around you could try to fix the immediate problem that the compiler detects by adding an ampersand at the front. So this is going to say, can I please take a read-only reference to numbers? Then we get a complaint about immutability. So I'm just going to keep moving because we could try and get ourselves unstuck, but essentially we'll detect that it's impossible, that we will not be able to force Rust to be able to iterate something and mutate it at the same time, or at least add or remove elements inside the list. We can, in fact, I think even the stronger assertion around mutation is true too. Here's a fun one. JavaScript. I mean, everyone loves to complain about JavaScript. So the computer scientists in the room will know that the set data type, one of its properties is that it removes duplicates. And therefore, if two things attempt to be inserted into a set that are equivalent, only one of them should remain. It turns out, though, that JavaScript equality semantics are slightly misleading. My understanding is that they actually refer to the address space in memory, which is something that I care about a lot when I program in JavaScript. Rust will force you to choose. So let's see what I mean. So here we have a collection, we've got a set, and I've created my object, and it contains an ID field. So Rust is going to be less friendly at kind of dynamically creating data structures. I kind of need to create a struct myself. And then let's see if I can compile this. It's going to say no. Let's say that it doesn't implement this trait thing. So one way to read this, if you're from an object-oriented background, would be to say that Rust, or this object type, or this object struct type, doesn't inherit from equality. So we can ask Rust to do something for us. We can ask the compiler to actually derive equality. And in fact, equality requires this sort of sub-trait called partial equality because of the way that floating point works. Turns out not a number means that for floating point, there is not a numbers always compare as unequal, even if the bit patterns are the same. And for that reason, there are these kind of weird, there's two traits. Now we're also being asked for another one, which is hash. Once this compiles, we get 1. So the size of the set after 2 insertions is 1, which is kind of a semantic meaning that's closer to what we expect. We actually get to choose. We could manually implement equality and say that what we really care about when we mean equality is like the state of the universe or something. If we break the trust that the type system provides, we can do whatever we want. Lastly, and I don't mean to pick on Go, but a lot of people compare Rust and Go, so I thought that I would do the same. So Go, in this program, what we're doing is we're printing hello world. We're printing a map, and the name that we're printing as our default is world. And then we spawn 2 Go routines, Tim and Tom. So the question for the audience is, like, what are we printing at the end? It's not actually a trick question. It turns out this is completely non-deterministic. We don't know. It's up to the Go scheduler at runtime and the random seed that is created when it initializes as to what actually prints out. Rust will not be happy with a program like this. Rust is really going to want you to specify exactly what you mean when you provide shared access to memory across threads. And it is only going to enable one location that has mutable read-write, let's say mutation, the ability to mutate. However, you can read from the same location. You can have multiple readers, but only one writer. So just in very broad, like this is my broad claim, that I feel that Rust is an empowering technology. It really creates a sense, because you have these guardrails around which programs, because a smaller subset of programs will compile. And the subset that compiles are kind of the valid programs, which is useful. We actually want to not have things crash at runtime. It kind of provides this mental freedom to experiment and explore. So we can kind of look at write-ups for users who have used the Rust language, and it turns out that Rust is really, really good. And here's one company who actually managed to save 300 virtual CPU cores for their service while providing a lower, medium, and actually lower tail latencies as well. So they actually improve the customer experience while removing 75% of their CPU usage and 95% of their memory usage, which for me is really important because this actually means that our claim as an industry around sustainability, our claims are actually potentially coming to fruition. I'm quite a big eco warrior, so hopefully you won't blame me for bringing up the sustainability angle. If you run the equivalent Lambda function in multiple runtimes, you'll detect that Rust tends to outperform almost everything else available. And one claim that I make is that the Rust Lambda function that you write will have finished executing by the time that the Python interpreter has read your script. I can tell you in very broad terms about our experience at AWS. The bulk of AWS is written in Java, and particularly with the Corretto JVM. And teams that have experimented with the Java runtime find cold start latencies on the Lambda, somewhere 8 to 12 seconds. With Rust, this comes down at the cold start for, I think it's under a second. And then the response time in the warm state is, we're talking about single digit to small tens of millisecond responses consistently, which is ridiculously important for a company that is laser focused on cost. One of the public case studies provided by the Rust Foundation actually talks in very similar terms about Tilda's experience. So Tilda is a startup, and they have a little service that requires a runtime agent on their clients' compute instances. It turns out that when your agent takes, let's say, 100 megs at steady state, people start to notice and complain. And it turns out that multiple people were complaining about this agent because it turns out that they were living inside Heroku and they would like hit the ceilings. Rust enabled Tilda to effectively just turn their agent into something that is more or less invisible from an operations standpoint for their customers. And by the way, the stuff that's kind of behind the curtains, their server appliance, used to require a 5 gigabyte steady state memory, and that was shrunk all the way down to 50 megs. This example here is from Discord. So the Discord blog has a very detailed introduction to the comparison between Go and Rust. It's quite hard to detect there is a purple line, or there are 4 purple lines and 4 blue lines. The purple is Go, and the blue is Rust. It turns out that the garbage collection pauses under heavy contention introduced very significant CPU spikes every 2 seconds, which resulted in their customers experience a relatively large amount of pain because suddenly your tail latencies hit hundreds of milliseconds. And in fact, the P100s for the Go service there are over like 3 or 4 seconds in some cases. Whereas in their Rust, we've reduced that to, it looks like under 2 at the worst case. So I just kind of wanted to geek out a little bit. I've got kind of like an advanced feature. I don't know if anyone has played with operating systems, but I thought I'd introduce inline assembly just as, because you can. Let's say that I wanted to, just to make it very clear, the point is that Rust is a systems language, or at least it emerged in the systems paradigm, and does enable you to sort of peel back every layer if you'd like to. But this is ASM for assembler, and we're talking about x86 assembler, so we're using shifts and with shift left and addition to implement multiply by 6. So we give it a U64 and we get a U64 out, or at least that's kind of what it looks like. So let's try this. We're going to get a compile error saying, hey Tim, you're trying to mutate X. So even when you're using inline assembly, you still get Rust's safeguards. And by the way, we can now calculate 5 times 6 is 30, so well done Rust. I'll just touch on very briefly a couple of the services that we've implemented. Rust is now a very mainstream language. In fact, I'm paid to support Rust in the company. And if you're CloudFront, so this is the CDN product from AWS, you get asked a lot to implement HTTP3. This is something that they were really anxious about, and they ended up creating an open source package called S2N-Quick. So the quick implementation, or HTTP3, which is HTTP essentially over a UDP instead of TCP, is now implemented in Rust. Firecracker is the virtual machine technology, or it is micro VMs. So I'm just thinking about the angry emails that I'm going to receive from my colleagues at work by describing or failing to describe correctly what Firecracker is. It is a virtualization system which enables Lambda and Fargate. So every time you've ever worked with serverless at AWS, you've driven it with Rust. The Prime Video application, so the client application, is completely different. So this actually sits in away from AWS into Amazon land. And the Prime Video has a problem, and that is so this is the thing that sits on smart TVs. They need to support and test at least 8,000 different device types. And all the way from like things that are smaller than just kind of you fit in your hand, all the way through to the kind of relatively large desktop systems that also serve the client. It turns out that compiling to WebAssembly with Rust actually kind of broke through a couple of performance ceilings that were really starting to cause a lot of complaints. And once they kind of switched this on, there's a blog post from February that describes this process of suddenly you could kind of you could sense the impact that this had like in the contact center. Lastly, in S3, a new storage node. So S3 is actually quite a complicated architecture, but on the hosts that are serving the content, we call these storage nodes. A new type of backend is being re-implemented in Rust, this thing called shard store. It provides higher performance and higher reliability than extremely optimized Java. The S3 teams spend an incredible amount of energy trying to understand how to optimize their code, and the Rust implementation has been able to perform significantly better while also introducing the Rust community to formal verification. So if you've ever used mathematical provers or formal verifiers, you might have noticed that in Rust, there is now the Kani model checker and a couple of other projects which are linked to in this paper here as well, that Amazon has pushed into open source because they've enabled us to verify some of the claims that we're making around being able to recover from any failure possible. Sadly, though, it's just software, right? So I've made all these audacious claims around performance, and you're going to save 95% of memory, like all of this stuff. Sadly, like I've kind of got to. There's got to be a hook. Like there's got to be a catch. Sadly, there are still bugs. It doesn't catch everything. So here's something stupid to do, but something that's relatively fun. I've got a -1, and I've got an. So another way to write this would be something like that. So I've got an assigned integer that is -1, and then I want to cast that as an unsigned. And then like Rust happily compiles that, because this is the bit pattern of -1 in memory as an unsigned integer. And I can say, like, I'm running, what other tools do I have? It turns out this integer casting in Rust is a little bit different if you've ever used C. In C, things will types will automatically be promoted to fit, and this causes really subtle, irritating bugs. Rust will require that all casting is explicit, but that doesn't actually provide you with a whole bunch of security if you have contexts like this, especially around overflowing or between types. So the problem that I've described, or I'm trying to describe, is that this is compiling onto a, the problem is basic, I32, no. The problem really is that usize, which is an unsigned integer of the width that relates to the target platform. So on a 64-bit CPU, it's 64-bit wide. But let's say on a microcontroller, it might be 8 bits, or actually, let's say 16 bits wide. Doesn't represent negative numbers. So instead, I can opt into using a slightly more angry syntax, which is this try into, which will attempt to apply the conversion and return what we call a result at the end of it. And I can try and unwrap it and say, Rust, I know that inside that result that you provide me is going to be a happy integer. The type hint is provided over here on the left. And it turns out that that breaks, which is actually what we want. For like numerical conversions, we would rather the program kind of blows up in our face rather than just creating something that's mathematically invalid. There are a couple of other things which I think are potentially wrong is too strong, but there are some lessons that the Rust community has learned over time around effective use of the technology. And one of the things it's learning is how to teach. So if you go and ask the developers, we heard 7 years in a row, the developers, people really want to program in Rust. They're really excited about it. Then some people try and read the documentation online, they buy a couple of books, and they just give up. Right? They just walk out. It's like, this sucks. I hate it. That kind of, I hate it, I'm out experience is common. And if you ask people who have left the Rust community in the surveys why they did, it turns out that a small majority relate to the teaching experience. And so one of since I started in about 2015, the level of maturity around documentation at the beginning into immediate and advanced materials are significantly better all the way through from very guided resources through to kind of self-guided lab kind of content as well. One thing that I find really annoying is that it turns out that computers are difficult. And Rust has wonderful generics which provide really elegant code, but sadly we get into programs like this. So we'll kind of work from the inside out here. The thing that actually does the work is this U : from self. What this is a type conversion, a generic type conversion implementation. And now we're going to start back at the top. Impl, and I've got this square braces T and U. So I'm creating two type variables, T and U, within the context of this, what we call an impl block. And we're implementing the trait into, for U, for the type T. So what this enables us to do is convert from type T into type U. And Rust will automatically implement this trait for any type for which the type from is implemented for T to U, if that makes sense. So if you have already taught Rust how to program from one direction, it will actually create the implementation for the reverse direction. And I think it's telling that a function that is, about 10 characters long takes about 3 minutes to explain. And there are other parts of Rust that are really quite gritty. And brace yourself for this frustration. I don't want you to walk in expecting that you're just going to get it, because Rust will require a lot of upfront thinking, and there will be times at which you encounter documentation or source code that just kind of looks like this garbage. So here are some tips for avoiding cultural shock with Rust. First of all, it's a compiled program. So we start with some source code, and we end up with some sort of compiled result. But unlike sort of a Python or we don't have the REPL, we don't have this interactive prompt. So I need to invoke a Rust compiler. And I can typically, and this is going to sound ridiculous when I speak it, I use a tool called Cargo to invoke the Rust compiler. Cargo knows about the context of my project, about where dependencies come from. It will go and download those dependencies on my behalf and link them all together and send the right stuff to Rust-C, the Rust compiler. And then the compiler kind of does its thing, and this chain all works together almost magically. But I want you to remember that the process is different. If you're used to, say, a Ruby or a JavaScript, it doesn't quite feel as seamless because there is a step where the cogs are turning and you're waiting for the thing to work. I mentioned Cargo before. You'll kind of find a small family of tools that are extremely useful once you start using them, but actually are just more things to learn when you're starting out. And that's a problem because you actually just want to go like sort of one learning curve at a time, but it turns out that you need to kind of learn 6 at the same time. And that's not very, from a working memory point of view, that's not amazing. Cargo, by the way, is what you sort of interactive with to kind of manage your project. And Clippy is a linter. Yes, it is named after Microsoft Clippy. And much more helpful, let's say, than the Office utility. And Rust format will supply a negative way to say this would be it will coerce your program to comply with the Rust conventions for formatting. There are actually a few knobs and dials to configure the Rust formatter for your particular project, but it's relatively rare because the formatting is, by and large, consistent across the entire ecosystem. If you are from a systems background, or if you have, let's say, programmed in Java or C#, and you might be thinking, like, where are objects being allocated? Rust is very stack heavy. And let me contrast with Java or like a C#. In a managed world, your object will be allocated on the heap, and a reference to that object will be allocated or will be inserted as a local variable on the stack. Once a garbage collection pause runs either whether or not you use reference counting or generational garbage collection, if there are no more references to the objects on the heap, they get cleared or marked as free. Rust will prefer to provide values on the stack itself because it knows about how wide things are in memory. This provides a significant performance gain because of the way that CPU architecture, the way that chips are actually created these days, which is that memory does not sit, we access it in some sort of linear fashion from within a virtualized address space, but actually it turns out that there's a very strong hierarchy of memory layout where your L1 cache is orders of magnitude faster than main memory, which itself is orders of magnitude faster than disk. Therefore, if we can keep things in cache or even inside registers, which is enabled by keeping variables on the stack, your programs will automatically run faster. The downside is that you need to be extremely pedantic with where things are, which is why some of those irritations with Rust kind of come into play. Rust is going to care about whether or not your type is quote unquote copy or has copy semantics versus move semantics, because it wants to know that all references to that object are valid. And it will guarantee that validity at runtime. It does that with a feature called ownership, or feature is perhaps the wrong word. So the Rust ownership model is that every variable has one place in which is the owner. Think of an owning scope, perhaps. So and we think of ownership and property rights and kind of, then we get ourselves into a linguistic trap. Because the owner in Rust has only one job. It can't actually issue trespass notices or do anything like that. The only thing an owner can do in Rust is to delete objects that it owns. So it's almost a misnamed concept, because what is really controlling access are these read-only references versus, and there's another form, like a mutable, well, this is going to sound silly, but we can create a read-write reference as well, called a mutable borrow, versus a read-only reference would be normally referred to as just a read borrow. And the ownership system is implemented by essentially a logic solver in the Rust compiler. So this will all fade away and at runtime. There'll be no extra bits that are checking who is the owner at this given moment in time in your program. Rust has the ability to check that irrespective of where variables are living and which threads have access to them, that the the lifetime of those objects is the right place for for every point in the program, every variable has not just a type, but also a lifetime. The Rust will require that any access to those variables occurs within that valid lifetime. At the end of the lifetime, the owner of the variable will delete that variable. In Rust terminology, this is called dropping. And therefore, Rust will complain very loudly, very quickly, if you are attempting to access data that is no longer valid or is not yet been initialized. I want to just very briefly, as we sort of hit getting close to the wrap-up stage, one piece from Nature. So this was a sort of a column, I suppose you might say, but it has been peer-reviewed, so it's relatively good. It's talking about how scientists use programming languages and this kind of desire to create, data-driven science requires very effective processing, but the problem with C and C++, which was the standard tooling, perhaps maybe a Fortran, is that they're not very nice to use. They typically would love Python and just make Python go faster. They don't provide guardrails, which Rust does. And they actually cite the Microsoft post that came in earlier in the talk. It describes a little bit how ownership works in probably a more elegant way than I was able to just before. And just want to emphasize the last sentence that an entire class of correctness areas just go away by design. For me, however, the reason why I've sort of stuck with Rust is that I find the Rust community to be exceptionally inclusive and to be kind of values-laden in a very positive way. And that, to me, is one of the reasons that I've kind of stuck around. I learned Rust because I was hitting the boundaries with Python, and I really wanted to understand how computers worked. Rust kind of taught me what a pointer was. But actually, it's also taught me how to contribute or kind of create open source ecosystems that are healthy and vibrant. The safety angle, particularly if you are a large business with customers who are paying you for software, kind of should be enough. I find that a really compelling and very persuasive argument. But it turns out that there's more. You actually get to benefit too as the person who is the service provider. Your programs are more stable. They are going to be able to use less compute resources, which means that they are cheaper to run. I also like that they are going to require less energy to run, which is going to have a net benefit for the world's compute ecological footprint as well. Lastly, the Rust compiler is surprisingly helpful. The Rust community is vibrant and inclusive. If not Rust, then you're more than welcome to take some of those attributes and inject that enthusiasm and that support to some other community where you kind of feel that this kind of human-centric view of computing is lacking. If you are the project leader of the world's most operating system kernel for the world's most popular operating system, the threshold for introducing a new programming language is fairly high. I encourage you to kind of look at look at the Rust in Linux kernel as a model for how you might consider prototyping Rust at work, or even for your own projects. So Rust was introduced to Linux completely to the side of the mainstream or the mainline programming effort. And even now, even though it is being included in the kernel, it relates to drivers and projects that kind of need to prove their worth. The burden should be on Rust, the burden of proof should be on Rust to be able to deliver on these promises of performance and safety. And therefore, my recommendation is always to find some sort of piece of the business that where there's like, let's say, a performance issue, or you know that there's something that needs fixing, but which you have a really good understanding of the problem domain. Do not make the mistake of attempting to learn a programming language and like a new piece of business functionality at the same time. Like, that path is pain. With all that in mind, though, I really hope that you've enjoyed this afternoon's session, and I'm looking forward to seeing what everyone can do with Rust and with whichever programming language they'd prefer. Thanks.
We might have time for a question or two. Hands up if you had a question. Oh, thank you at the front.
Thanks for that. So just from what you were saying, Rust has the concept of variables. Variables have a lifetime, and an owner is responsible for releasing that memory. Was Rust the language that invented that concept, or did it come from somewhere else?
No, so one of the really interesting things is that we've got this concept. It actually didn't, it emerged as mainstream with Rust, but it was in research languages, I think, going back to the 70s. This idea that you could actually annotate variables with a lifetime is not a novel concept. There's a really fascinating talk from 2012 from Graydon Hall, the original creator of Rust, who just sort of describes that his intention was to have no novel features, no genuine novelty in Rust, because it was intended from the outset as being a production language. Mozilla was facing an existential threat with the growth of Chrome. They couldn't enable parallelism inside Firefox. They needed a new programming language. Only features that could really enable that kind of got into the language. And there was nothing genuinely novel from a computer science point of view.
Amazing. One more question, and then we might call it after that so you can make your next session.
So I'm one of the people that tried learning Rust and then walked away. How long did it take you to love the borrow checker?
Okay, so the question was how long did it take to learn the love? I don't know if I do. Okay, so the borrow checker is this component that is checking all of your references that they actually fit within the lifetimes properly. It turns out that this, on the surface level, at least conceptually, should be simple. But people will find, if they use patterns that they're used to from their other programming experience, that they'll kind of get themselves into knots. So there's this cliche of fighting the borrow checker. Now, the question is when did you kind of learn to love it? It's not so much that as becoming more familiar with understanding where my data starts and where ownership originates, and being able to mentally track where things are as the program evolves, or so for example, one of the things that Rust does really badly is graph data structures. It's really, really impossible to have an undirected graph in safe Rust because ownership is ambiguous by design. So the one way out of this is to kind of have let's say a manager object, which kind of is a supervisor across all the nodes. So you kind of insert this thing where ownership lives, that actually isn't related directly to the graph. And therefore, all of the references that exist like within the graph actually kind of relate more to the ownership of this kind of manager. And there are some strategies that kind of come through once you have some experience with the language. There are some other things as well. So typically, you kind of learn that actually it's okay to copy some data. So I don't always need to point back to one thing. I can actually copy and clone objects around. Computers are very, very, very fast. And if you think about the count words example, the equivalent Python code would probably take hundreds of memory allocations just to do that same process. Rust has 0. A memory allocation, let's say, is on the order of, let's say, somewhere between 20 and 100 microseconds. So Rust is going to have an immediately performance benefit, even if there was like no runtime in Python land as well. And in terms of the borrow checker, there are some patterns that you kind of become accustomed to and some design patterns for the larger, like bigger projects that do become easier. You're kind of cutting with the grain instead of against the grain, let's say.